In elementary algebra, the binomial theorem describes the algebraic expansion of powers of a binomial, hence it is referred to as binomial expansion. According to the theorem, it is possible to expand the power into a sum involving terms of the form axbyc, where the exponents b and c are non-negative integers with b plus c equals n, and the coefficient a of each term is a specific positive integer depending on n and b. When an exponent is 0, the corresponding power is usually omitted from the term. For example, the coefficient in the term of axbyc is known as the binomial coefficient or. These coefficients for varying n and b can be arranged to form Pascal's triangle. These numbers also arise in combinatorics, where it gives the number of different combinations of b elements that can be chosen from an n-element set. History. This formula and the triangular arrangement of the binomial coefficients are often attributed to Blaise Pascal, who described them in the 17th century, but they were known to many mathematicians who preceded him. For instance, the 4th century BC Greek mathematician Euclid mentioned the special case of the binomial theorem for exponenta too, as did the 3rd century BC Indian mathematician Pingala to higher orders. A more general binomial theorem and the so-called Pascal's triangle were known in the 10th century AD to Indian mathematician Hulaida. Persian mathematician Al-Khawarizmi, in the 11th century, was aware of a more general binomial theorem, along with Persian poet and mathematician Omar Khayyam, and in the 13th century to Chinese mathematician Yang Hui, who all derived similar results. Al-Khawarizmi also provided a mathematical proof of both the binomial theorem and Pascal's triangle, using a primitive form of mathematical induction. Sir Isaac Newton is generally credited with the generalized binomial theorem, valid for any rational exponent. Statement of the theorem. According to the theorem, it is possible to expand any power of z plus ay into a sum of the form, where each is a specific positive integer known as a binomial coefficient. This formula is also referred to as the binomial formula or the binomial identity. Using summation notation, it can be written as: the final expression follows from the previous one by the symmetry of x and y in the first expression, and by comparison it follows that the sequence of binomial coefficients in the formula is symmetrical. A simple variant of the binomial formula is obtained by substituting 1 for y, so that it involves only a single variable. In this form, the formula reads: or equivalently. Examples. The most basic example of the binomial theorem is the formula for the square of z plus ay. The binomial coefficients 1, 2, 1 appearing in this expansion correspond to the third row of Pascal's triangle. The coefficients of higher powers of z plus ay correspond to later rows of the triangle. Notice that, the powers of x go down until it reaches 0, starting value is n, the powers of y go up from 0 until it reaches n. The nth row of the Pascal's triangle will be the coefficients of the expanded binomial. For each line, the number of products is equal to, for each line, the number of product groups is equal to. The binomial theorem can be applied to the powers of any binomial. For example, for a binomial involving subtraction, the theorem can be applied as long as the opposite of the second term is used. This has the effect of changing the sign of every other term in the expansion. Another useful example is that of the expansion of the following square roots. Geometric explanation. For positive values of a and b, the binomial theorem with now equals a2 is the geometrically evident fact that a square of side a plus b can be cut into a square of side a square of side b, and two rectangles with sides a and b. With now equals a3, the theorem states that a cube of side a plus b can be cut into a cube of side a cube of side b, 3 or b rectangular boxes, and 3 or b rectangular boxes. In calculus, this picture also gives a geometric proof of the derivative of one sets and interpreting b as an infinitesimal change in a, then this picture showed the infinitesimal change in the volume of an n-dimensional hypercube, where the coefficient of the linear term is the area of the n faces, each of dimension. Substituting this into the definition of the derivative via a difference quotient and taking limits means that the higher order terms a euro and higher a euro become negligible, and yields the formula interpreted as, the infinitesimal change in volume of an n-cube as side length varies as the area of n of its dimensional faces. If one integrates this picture, which corresponds to applying the fundamental theorem of calculus, one obtains Cavaliere's quadrature formula. The integral c proof of Cavaliere's quadrature formula for details. The binomial coefficients. The coefficients that appear in the binomial expansion are called binomial coefficients. These are usually written, and pronounced o and choose euro. Formulae, the coefficient of exponent is given by the formula, which is defined in terms of the factorial function n. Equivalently, this formula can be written with k factors in both the numerator and denominator of the fraction. Note that, although this formula involves a fraction, the binomial coefficient is actually an integer. Combinatorial interpretation. The binomial coefficient can be interpreted as the number of ways to choose k elements from an n-element set. This is related to binomials for the following reason: if we write n as a product, then, according to the distributive law, there will be one term in the expansion for each choice of either x or y from each of the binomials of the product. For example, there will only be one term xn, corresponding to choosing x from each binomial. However, there will be several terms of the form xna2y2, one for each way of choosing exactly two binomials to contribute a y. Therefore, after combining like terms, the coefficient of xna2y2 will be equal to the number of ways to choose exactly two elements from an n-element set. Proofs. Combinatorial proof. Example, the coefficient of xy2 in equals because there are three x, y strings of length 3 with exactly two y's, namely, corresponding to the three two-element subsets of A1, A2, A3, namely, where each subset specifies the positions of the y in a corresponding string. General case, expanding yields the sum of the two an products of the form E1 E2a. An an where each ai is x or a y. Rearranging factors shows that each product equals x and a for some k between 0 and n. For a given k, the following are proved equal in succession: the number of copies of x and a in the expansion, the number of n-character x, y strings having y in exactly k positions, the number of k-element subsets of A1, A2, an. This proves the binomial theorem. Inductive proof. Induction yields another proof of the binomial theorem. 1. When I equals A0, both sides equal 1, since xo equals A1 and. Now suppose that holds for a given n. We will prove it for n plus A1. For j, a permil beta 0, let e, x, ay, ajk denote the coefficient of xjyk in the polynomial e, x, ay. By the inductive hypothesis, n is a polynomial in x and y such that, za plus ay, n, aj, k is if jar plus a chi equals an, and 0 otherwise. The identity shows than plus 1 also is a polynomial in x and y, and if jar plus a chi equals an r plus a1, theta plus a chi equals an and jar plus a, chi a1, equals an, so the right-hand side is by Pascal's identity. On the other hand, if jar plus chi permil and r plus a1, theta plus a chi permil an and jar plus chi euro a1, a permil an, so we get 0 plus a0 equals a0. Thus, which is the inductive hypothesis with n plus a1 substituted for n and so completes the inductive step. Generalizations, Newton's generalized binomial theorem. Around 1665, Isaac Newton generalized the formula to allow real exponents other than non-negative integers, and in fact it can be generalized further, to complex exponents. In this generalization, the finite sum is replaced by an infinite series. In order to do this, one needs to give meaning to binomial coefficients with an arbitrary upper index, which cannot be done using the above formula with factorials. However, factoring out from numerator and denominator in that formula, and replacing n by a, which now stands for an arbitrary number, one can define. Where is the proclammer symbol here standing for a falling factorial? Then, if x and y are real numbers with xaay, and r is any complex number, one has. When r is a non-negative integer, the binomial coefficients for k are 0, so specializes to, and there are at most r plus a1 non-zero terms. For other values of r, the series has infinitely many non-zero terms, at least if x and y are non-zero. This is important when one is working with infinite series and would like to represent them in terms of generalized hypergeometric functions. Taking r equals aas leads to a useful formula. Further specializing to r equals a1 yields the geometric series formula. Generalizations formula can be generalized to the case where x and y are complex numbers. For this version, one should assume xaay and define the powers of z plus ay and x using a holomorphic branch of log defined on an open disk of radius x centered at x. Formula is valid also for elements x and y of a Banach algebra as long as xi equals x, z is invertible, and a y xaa1. The Multinomial Theorem. The binomial theorem can be generalized to include powers of sums with more than two terms. The general version is where the summation is taken over all sequences of non-negative integer indices k1 through km such that the sum of all key ic and the coefficients are known as multinomial coefficients, and can be computed by the formula. Combinatorially, the multinomial coefficient counts the number of different ways to partition an n-element set into disjoint subsets of sizes k1, a km. The multibinomial theorem. It is often useful when working in more dimensions, to deal with products of binomial expressions. By the binomial theorem this is equal to. This may be written more concisely, by multi-index notation, as applications, multiple angle identities. For the complex numbers the binomial theorem can be combined with de Moivre's formula to yield multiple angle formulas for the sine and cosine. According to de Moivre's formula, using the binomial theorem, the expression on the right can be expanded, and then the real and imaginary parts can be taken to yield formulas for cos, nx, and sin, nx. For example, since de Moivre's formula tells us that which are the usual double angle identities. Similarly, since de Moivre's formula yields in general and series for E. The number E is often defined by the formula. Applying the binomial theorem to this expression yields the usual infinite series for E. In particular, the kth term of this sum is as NaAAA, the rational expression on the right approaches 1, and therefore, this indicates that E can be written as a series. Indeed, since each term of the binomial expansion is an increasing function of n, it follows from the monotone convergence theorem for series that the sum of this infinite series is equal to E. Derivative of the power function. In finding the derivative of the power function, f x equals xn, by using the definition of derivative, the expansion OFN is employed. Nth derivative of a product. To indicate the formula for the derivative of order n of the product of two functions, the formula of the binomial theorem is used symbolically. The binomial theorem in abstract algebra formula is valid more generally for any elements x and y of a summaring satisfying xi equals x. The theorem is true even more generally, alternativity suffices in place of associativity. The binomial theorem can be stated by saying that the polynomial sequence A1, AX, AX2, AX3, A is of binomial type. In popular culture, the binomial theorem is mentioned in the Major General's song in the comic opera The Pirates of Penzance. Professor Moriarty is described by Sherlock Holmes as having written a treatise on the binomial theorem. See also, binomial approximation, binomial distribution, binomial inverse theorem, binomial probability, binomial series, combination, multinomial theorem, negative binomial distribution, Pascal's triangle, Stirling's approximation, notes. References External links: Solomontsov, ed., Newton Binomial, in Haswinkel, Mikhail, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Binomial Theorem by Stephen Wolfram, and Binomial Theorem by Bruce Coletti and Jeff Bryant, Wolfram Demonstrations Project, 2007. This article incorporates material from Inductive Proof of Binomial Theorem on Planet Math, which is licensed under the Creative Commons Attribution Share Alike license.